Okay, welcome to this video. This is a debate around pressure and barometers between me, Toady, who is reasonably well known now on the scene, and this character here, who we believe to be Spurskimo. I'm responding to challenges from Spurs on a number of hangouts and debates. This relates to pressure and its practical demonstration. Okay, the claims that have been made by Spurskimo and Right the Hand. Let's go through them just to recap what they've said on a number of hangouts and in a number of forums. First of all, that there is no such thing as atmospheric pressure, or indeed, Right the Hand also says it's inconsequential. Secondly, the so-called effects of atmospheric pressure are actually due to temperature. Thirdly, altering pressure will increase or decrease, depending which hangout it is, the temperature. Fourthly, pressure is linked to the water that is in the air or other gas and liquid, which doesn't seem to make much sense, but it is indeed what they have said. And then finally, that barometers cannot work at low temperatures because the metals freeze. When asked about the metals, Spurs just said that they were standard metals. So moving on, we're under pressure now, I think, in our community to respond to this. What are we going to do? We're going to recap on a few of the basic concepts around pressure and indeed how it works. Much of that material actually has been extracted from standard high school physics books, my son's physics book in fact, to help set the standard context. The interesting thing when I've looked at those physics books or notes is that they do contain an amount of maths and some formulas, but actually, unlike the argument from a lot of the flat earthers and from Spurs himself that we just learn parroting things and it's just learned by rote, in fact there's a number of questions there that makes the student question what the relationship is and what the phenomenon is and what the cause and effect indeed is. So there certainly isn't any rote learning there, and it's a shame maybe that Right the Hand and Spurskimo don't go back and do a basic physics course. I think it would improve their understanding significantly. The notes will cover the history of atmospheric pressure, how we define pressure, how we measure pressure, the difference between gauge and atmospheric pressure, which is often misunderstood and it's an easy mistake to make, and we'll touch on that, the various types of barometers that there are, and indeed the aneroid barometer in detail, and this here is an aneroid barometer, and I bought one that's virtually identical. And then finally, we'll show a video which includes an experimental one. Now, I need to thank a few people for helping me to put this presentation, this video together. That is the Rumpus, George Hanetiuk, Farmer's Boy, Brian, and indeed Dean or Stingray. All of them helped me assemble this material, and I'm very thankful for their help. It was a community effort. Okay, let's dive straight into it. What is atmospheric pressure? Well, air pressure is measured in newtons per meter squared, Pascal, or pounds per inch, which we're much more familiar with. That's the old PSI. Now, essentially, we're surrounded by an ocean of air. And so air pressure really is the amount of air that is above us that's pushing down onto us or into the surface that we're measuring against. So the pressure at the surface of the Earth is not something that's arbitrary. It's not an arbitrary measure on a scale that someone has just randomly invented. It actually is what we term as 1 atmosphere, and it amounts to a pretty consistent measure of the amount of air pressure at the point of sea level at certain normalized temperatures. Now that happens to be 14.696 psi, as we can see stated here, often called 14.7 psi. That's either 1 atmosphere as well, or indeed it's 101.325 kilopascals, as we can see here. Just to put all of that in context, because I think we probably need to, dry air, so that's dry air, not wet air, but dry air, because obviously wet air can vary a lot, but dry air has a density of 1.2 kilograms per meter cubed. So if you imagine you could take a meter cubed of air and you could weigh that, it would weigh about 1 kilogram. So, you know, it's a quite significant weight. We think of air as quite insubstantial. It's not. Okay, moving on. We see here a really nice picture, and I included it. It's from Douglas Seeger's Introduction to Ocean Sciences. There's a call out here at the bottom of where it came from. And we see this really nice picture actually of the troposphere, ozone layers, all the way up to the stratosphere and the mesosphere, which really shows the whole of our atmosphere. We can see where the jets tend to fly at about sort of 13, 14 kilometers up. And we can also see this line here, the red one, and this line here, the purple one. Now the purple one is pressure, and the red one is temperature. And the beauty of seeing this is we can see that there's a relationship between both of them, and we can see indeed that as temperature drops, there's also a change in pressure, so we can see that the two are indeed related, but we can also see that there is clearly not a one-to-one relationship between the two. When Spurs says that pressure is temperature and temperature is pressure, we can clearly see that that is not the case from these typical measurements that we see here on this view. Okay, and you can also see obviously the sheer amount of air that is above us. If we are down here, on the surface of the globe, we can see that there's a huge amount of air up above us. Up to 60 kilometers worth of air. Obviously getting thinner, but up to 60 kilometers worth of air. All right, let's move on to the measurement gauges and the barometer. So this we see here is a mercury barometer. This was developed by Toricelli, and we'll touch on him a little bit later. And he did this to measure atmospheric pressure. In fact, he was actually trying to solve a problem to do with pumps in the area that he lived in Italy. They were making these pumps, and they couldn't actually get water to pump above, I think it was about 34 feet, something like that, maybe 34, 39 feet. They had this problem. They make these pumps. They couldn't pump water above that height, and they called on Toricelli to have a look at it, and he came up with a barometer. Now, the height of the column of mercury is such that the pressure in the tube at the surface level is 1 atmosphere. So the beauty we have here is we have a tube. We put mercury into the bath below. The mercury goes into the tube, and the weight of the atmosphere that is above the bearing, the surface area here, where it is open within this bucket or container, pushes against it, and it pushes the mercury up to a height, in this case, of 76 centimeters. Now, this is mercury. Obviously, the heights will vary, and we'll touch on that if you used water or oil or other substances. I think there's a thing called the shark oil tube, which is even less dense, I think, than water from memory, and is a very exciting thing that you can see somewhere in America. So, different substances, different liquids can be used for making this, and they will all vary depending on the density of the substance used. Now, because this is 76 centimeters, or much better, 760 millimeters, pressure is often quoted in millimeters, but you can also do inches of mercury. So moving on, let's look closely at this barometer. So barometers measure atmospheric pressure. I mean, that's obvious. One type of barometer, the one that we're showing here, uses this column of liquid, and it's mounted in a reservoir which is open to the atmosphere, as I described earlier. The pressure exerted by the column is given by this formula, and we'll come back to this formula. It's a very important one. Pressure, absolute in this case, equals H times rho times G. Now, what are these? Rho is the density of the liquid that you're using. G is acceleration due to gravity, which we already know is 9.81 meters per second squared. And H is the resulting height of the fluid above the reservoir. And so we can use this in different formulations of this formula to work out different things. So if we know the density of a liquid, let's say it was water, and if we know the atmospheric pressure, and if we also know what the density of that liquid is, we can actually work out what height we would need for our barometer. And indeed, we'll see a touch on that in a sec. So atmospheric pressure is equal to 1.013 10 to the 5 newtons per meter squared. Now, for a mercury column, that is, as we said before, 760 millimeters in height. Yeah, so that's very convenient because mercury is a nice dense liquid, so we don't need a lot of it. So we can make a barometer that is less than a meter high, because we don't want sort of 50-meter barometers. And we will touch on this later when we come to the water column. That's much less dense than mercury, so therefore the column that we make to be able to measure just 1 atmosphere is much, much higher. So here we see exactly what I've been just talking about there. This is Toricelli's original barometer, and you can see it's massive. It goes right out the side of this house. They've built some kind of structure and framework. There's a guy in the window pointing at it. It's all quite exciting, and he's doing this experiment in the market square. It took him a long time to blow that glass to get it straight, and all sorts of things to seal it off at the top. But really here he's doing the experiment, and here he is proving the fact that if you use water, which is of course less dense than mercury, you're going to need a very, very tall column. And indeed, at normal atmosphere, and at normal temperatures, so 1 atmosphere, normalized temperatures, we are not able to push this column above, I think it's about 30 odd feet, and we'll come to the exact measurement shortly. So barometric pressure ranges, let's look at them. So typically it's 28 to 32 inches of mercury. I prefer obviously the imperial system because us in Europe we use that a lot. So 711 millimeters to 813 millimeters of Hg, and indeed you'll see that on the aneroid barometer later, or 13.75 psi to 15.72 psi, and that is standard atmospheric pressure, and it ranges between these two values depending whether it's low pressure or high pressure, what the weather systems are doing across the surface of the Earth. Now, if we use water, which is what I spoke about earlier, instead of mercury, we have this formula. So the pressure is equal to 1 atmosphere. We're assuming this is a normalized standard atmospheric pressure. And then we have our G times H times rho. Now, as I said, rho is the density of indeed water, which we put into the equation here. G is 9.8 meters per second because of gravity. And of course, we want to calculate the height. So we move the height to the side, move the P over here, which is why we're dividing by it. So we divide all that through, we get to, I think what I said was about 34 feet, so 33.9 feet high. And indeed, that was the height of Toricelli's column. Very, very high. And then finally at the bottom, we've just got the standard here. We've got 1 atmosphere is equal to 760 millimeters of mercury, 29.9 inches of mercury, 101.325 kilopascals, or indeed 14.696 psi. And all of those are the same. So let's move on to pressure gauges. So an open tube manometer is a type of pressure gauge. One end of it is open to the atmosphere and the other end is subjected to whatever we're testing, whatever the test pressure is. Now the liquid in the manometer will rise until the pressure exerted by the column matches the test pressure. And this is given by the formula P equals delta H, i.e. changing the height, times rho times G, where delta H is the height of the column, changing the height of the column. P is the density of the liquid, as we saw before, and G is acceleration due to gravity. Now, what's great about this is it already has, because this tube is open here, the normalized atmospheric pressure, which is pressing down upon it. So what we're able to do is we're able to see from this pressure gauge what the change in the pressure is with already the atmospheric built in. Now, I know a lot of people got confused around car tires that had pressure in or didn't have pressure. Did they include atmospheric or didn't they? We're going to cover all of that. This is a very, very simple way of measuring something whilst already including the atmospheric pressure into your gauge. And indeed, a lot of gauges do that, especially ones that measure PSI, because you don't want to have to keep remembering to add on what normalized atmospheric pressure is. Okay, here we go. Let's get into the difference between absolute and gas pressures. So we have P here, which is the absolute pressure, right? Absolute meaning the total or entirety of something. That is equal to the initial pressure, which is the atmospheric pressure that always exists, whether we're doing a measurement with whatever gauge it happens to be, plus our PGH, which we've covered before, which we call gauge pressure. So when we look at our manometer here, we already have P0. We already have, as I said earlier, the initial pressure or the atmospheric pressure, which is built in. So when we're measuring the pressure over here, this is the gauge pressure plus the atmospheric pressure, able to give us this, which is absolute pressure. Now, if you just want to know what gauge pressure is, that is delta P equal to PGH. So gauge pressure is the amount by which P exceeds the atmospheric pressure, which is P0. Really important point to make. So when we're measuring on our car tire that it's 20 psi, that's 20 psi gauge pressure, which of course you'd have to add on the standing atmospheric pressure of 14 psi, which would actually be in that example 34 psi. It's a really important point to make, really key slide here to explain the differences. So gauge pressure. Pressure gauges like tire gauges, the example I've just given, measure the difference between the atmospheric pressure and the internal pressure of the tire or balloon or whatever the test is. Remember, gauge pressure, PG, pressure of gauge, is always equal to the pressure that we're measuring minus the atmospheric pressure. So we always have to remember to include atmospheric pressure, depending what we're measuring, of course. Now let's look at a couple of ways of doing this. Here is a really good example. We have atmospheric pressure here at the top. We have the scale reading of our little tire gauge. We've got a little spring here to push against the pressure, and then we've got the pressure coming in from the tire, which might be, in my example, 20 psi. Of course, atmospheric pressure here already built in and being resisted. Now we're moving over here to a little bit more interesting area moving on. This is for measuring absolute pressure typically, and this is a aneroid barometer, and we're going to look a lot more closely about how this is constructed in a sec. So, detailed views of barometers and how they work. This is very similar to the one that I've just purchased. It's almost exactly the same, actually. You've got this needle here that you can move around, so you can do tests on where you last measured the pressure to. You've got this black needle that shows you what the pressure is measuring. And in this example, it would be 742 millimeters of mercury, which of course relates back to the mercury barometer that we saw earlier, though there is no mercury used in this device when it's measuring. And note actually the weather symbols that are on this variation of barometer. They're very, very useful so that we can see if it's a sunny day, we can see if it's likely to rain, because of course the pressure relates very much really to the weather conditions. Here we see a side view of the barometer. I think a cutaway orthographic view, very, very useful to see because we can understand how it works. What have we got? I'll talk you through it. We've got this sort of concertinaed piece of metal with a partial vacuum inside it, so a corrugated metal box. That responds and moves up and down. As it moves up and down, it bears against this spring. But as it bears against the spring, it also moves this pivot, which goes through a gearing mechanism essentially with a chain on it. It's a very tightly coiled spring here that then moves the pointer up and down as the obviously the corrugated metal box moves up and down. And we'll see that in a few more pictures here. Again, this is a sort of side cutaway view, quite nice 3D view. Again, we can see the vacuum chamber moving up and down. We can see the levering and the spring mechanism. By the way, all of these have been treated so that when the actual temperature changes, these don't change very much at all. So they're neutral to temperature changes up to certain measurements. And I'll show you what those are on the one I bought later on. But basically, you can't say, oh, well, it's temperature that's causing this pointer to move. It isn't. They normalize that through the choice of the materials here, where they use brass and tin and various other substances to make sure that they neutralize any effect of temperature. Here we see a very detailed cutaway view of a real life aneroid barometer. The pointer, we can see the corrugated area here. We can see all the springs and the coils and the chains going across, and we can see that it's quite nice and complicated. It's a finely made device and indeed finely calibrated. And finally, we go here to the specification of the barometer that I in fact used in my experiment, because Spurs said that I wouldn't be able to use it because I would be worried about the effects of the temperature that was occurring. And now that's not the case. I have indeed used it, and the one that I bought, it's not a very high-end one, it was relatively cheap, but as you can see here, it can go down to minus 20 degrees C and all the way up to 50 degrees C and still be measuring pressure. Great experiment for you. We've got a plastic bag, we've got a sweet jar, we have a thermometer that at the moment seems to be reading 25, 26, and we've got a barometer that measures in millimeters of Hg, which is mercury, and also HPAs. And that's a standard barometer showing, it's the black needle by the way, which is 100 and just short of 110, so maybe 108, something like that. But what I'm going to do is I'm going to put them inside this container, and then I'm going to apply pressure. And I don't think we'll see the temperature change, but let's try the experiment and see. Okay, so that's gone in the container now, as you can see. No pressure applied yet, of course. And then we also place the thermometer in there. And we can read both of those through the top, as you can see. Okay. Now all I'm going to do is I'm going to apply a pressure to this container using my hand, as follows. And we can see that the pressure goes up and down. Now I'm going to keep that pressure maintained, and we see that the temperature has not actually changed. It's still on 25. And indeed I'm still maintaining that pressure. Now what I'm going to do is I'm going to release that pressure, and we're going to see if the temperature drops at all. Are we ready? Now release the pressure that was applied, and the temperature hasn't changed one bit. Let's try that again. So I'm using my hand to apply pressure to this container. There we go, I'm pressurizing it. It's quite a bit of pressure I've applied there, turned it into a sunny day. And yet we see the temperature's staying exactly the same. Look, see if I can put a bit more pressure on. Oh, I'm really pushing really hard now. I think I might break the container in a sec. And still, the temperature's remaining the same. The pressure's now going to drop off as I release my hand, and we're going to see if the temperature drops off as well. Which of course it doesn't. I think that's QED. Thank you very much for watching. I'm just going to recap really what this video has shown and make sure that we summarize the findings. So first off, we've shown that atmospheric pressure exists and it absolutely can be measured using an aneroid barometer. You've already seen that in and out of the pressure sweet jar in which we tested it. Second, that gauge pressure is equal to total or absolute pressure minus atmospheric pressure. We showed that earlier on looking at the various equations and the way that different gauges worked. Thirdly, pressure change can be measured by a volume change within a container. We saw that with the sweet jar, we saw me change the volume, and we saw the corresponding pressure change on the aneroid barometer. Number 4. In this test, the change in the pressure does not measurably change the temperature. There's an important word there is measurably, but you saw that we changed the pressure up and down, and really we didn't see that particular thermometer move. And finally, a change in the pressure does not need water or air with water to occur. We didn't introduce anything into the sweet jar, nor did we need to. Thank you very much for your time. Thank you very much for watching, and I've been Toady.